questions. If you would like to ask some question, and if you are using Zoom, please click on this participant icon, and there you will see an icon for raising your hand virtually. And please wait for me to call your name to ask your question. And if you're using Cova, please write your question in the Q&A section on the right side of your screen, and I will read it to the speaker. So the first paper is BFair. Belma Turkovic will present the paper. Belma received her master's in electrical engineering from the University of Sarajevo. Currently, she is pursuing her PhD in the Embedded System and Network Systems group at Delft University of Technology. Her research focuses on programmable networks, network function virtualization, and tactile internet. Belma?
Yeah, hello. I'll try sharing my screen. Okay. Can everybody see my screen?
Yes.
Is it okay? Okay, great. So hello, everyone. My name is Belma, and I'm going to present our paper, BFair, Increasing Fairness Among Competing Congestion Control Algorithms. So let's first set a scene. Congestion control algorithms are a key component of transport layer protocols, and over the years, there have been many new proposals, each claiming superiority for specific applications or scenarios. Furthermore, new transport protocols such as QUIC enable quick development of new transport features directly from the user space, enabling thus even more customization and diversity in the future. Thus, due to this whole abundance in new protocols and algorithms, it has become almost impossible to take the coexistence and interactions of protocols with all the other ones into account when designing new algorithms. So as a consequence, even though when designing algorithms, good fairness properties are usually a priority, many papers have shown that multiple fairness issues exist. So this is especially true when the bottleneck links are shared between flows using different congestion control algorithms or flows having different round-trip times. So as we can see in this figure. So for example, if you look here, we can see that classic TCP flows that react to packet loss overpower congestion control algorithms that also take delay measurements into account by claiming almost all the resources. Similarly, even if we have all flows that use the same algorithm, like here, we can still have very low fairness if flows have different RTTs. And this usually increases if the difference in RTT between the flows is higher. Just due to these previously mentioned issues, so low fairness and many new algorithm proposals, in this paper, we decided to enforce the fairness from within the network itself. And we do that by grouping the flows based on their congestion control algorithm. Thus, we make use of the inherently good intra-fairness properties most flows are designed with. In addition, we want to do this from within the data plane using P4. So we want to be able to deploy our algorithms at the switches. However, to be able to deploy the algorithm on the switch, we have to take the limitations of the programmable hardware into account. So this usually means that we are restricted on the types of actions we can apply to packets, as well on the number of memory accesses we can have while the packet is being processed at the switch. So these limitations are usually imposed to make sure that these switches will run at line rate, so that there will be no performance degradation independently of the P4 program that we deploy on them. So to achieve this goal, we first started by analyzing the interactions between different algorithms in the Linux kernel. So if you look at this picture, we can see all the algorithms continuously probe for resources by increasing their sending rate until congestion is detected. So, sorry. So because all algorithms continuously probe by increasing their sending rate and they eventually detect congestion, so this usually is done either in form of packet loss or increase in the observed RTT or some combination of these metrics or some totally different metric. So we decided to use exactly this metric, so the one that's used to detect congestion, to divide algorithms into groups. So here we see our first group. So this is the loss algorithms, so the algorithms that only react to packet loss. Consequently, they're also the most aggressive algorithms. The most aggressive algorithms usually belong to this group. Second, we have algorithms that use an increase in the observed RTT, thus the delay as their primary metric. So they're usually very proactive, and they're among the least aggressive of the old analyzed algorithms. Next, we have old algorithms that are somewhere in between these, so that use some combination of these two metrics, which we here call loss delay algorithms. And finally, we had some algorithms that don't use the standard additive increase, multiplicative decrease algorithm. Instead, they try to build like a model of the network. So they use entirely different metrics. So now I'm going to explain the main basic building blocks of BFair. So the goal was to detect whether an algorithm belongs to the one of the four mentioned previous groups.
Hello?
Hello, I can no more see Belma's slides.
Yeah, me neither. She's offline.
She's offline, okay.
Well,
Can
actually,
we switch to the pre-recorded video?
yeah, I can do that.
Great, thanks.
Yeah, well, she's there, but well, but maybe it's not really there. She's not really there. Okay, give me 1 second.
Hello, I'm back again.
Okay.
Sorry.
Okay, if you're back, continue.
My PC actually, like my battery was dead. I didn't notice. Sorry.
Okay.
That's okay. Let's see if we can resume it.
Can you see it? Okay.
Yes, but in the speaker mode.
Okay. So this is where I was. So I'm going to go quickly through all the main building blocks of BFair. So if you look at the tradition,
sorry, can you move to the presentation mode? We are now watching your.
We are seeing the speaker mode with the notes
screen,
and everything.
maybe.
Oh wait, stop share. I shared probably the wrong screen.
Yeah.
Yeah. Okay. Sorry. God damn it.
Yeah, now.
Okay.
Thank you.
Yeah. Okay. Sorry for all the interruptions. So I'm going to explain the main ideas behind BFair. If you look at the picture of a typical programmable switch, you can see that switch typically has like an ingress and an egress pipeline with some packet queuing and scheduling in between. In the same way, BFair is also split between the ingress and the egress blocks and consists of 3 modules. So the first of these modules was a fingerprinting module, and the main purpose was to detect the congestion control group the flow belongs to, so the previously aforementioned groups. And we can see that this block was also split between the ingress and the egress block. So whenever a new packet was received by the switch, it was initially classified as a short-lived flow, as you can see here, and then the packets used involved in 3-way handshake were used to calculate the RTT of the flow. Next, the algorithm tried to determine the end of the slow start phase. And whenever it detected the end of the slow start phase, it's reclassified this flow into one of the long-lived groups, in this case, the least aggressive one, so the delay-based group. Finally, for all these long-lived flows, the algorithm tracks a set of metrics, such as the sending rate and queue length, and aggregates these metrics each RTT. So we decided to do this since most congestion control algorithms change their behavior each RTT, for example, to react to certain events or lack of them. And I'm going to explain this. So I'm going to explain this process a bit more detail on an example. So if you look at a typical cubic flow, at the beginning, cubic keeps increasing its sending rate. And it's classified as a mice flow, so a short-lived flow, so a flow that's still in the slow start phase. Whenever this flow, so the sending rate keeps increasing, and when it reaches its bandwidth delay product, BFair will reclassify this flow into one of the long-lived groups, so in this case, into the delay-based group, like I mentioned before. And now BFair will start tracking two additional metrics. So first one of these metrics is we call aggressiveness. So this metric tracks how fast the queue is being filled. So if the queue length increases, it also increases. Otherwise, it's reset to 0. And this is usually used to determine whether algorithms are loss-based, delay-based, or loss delay. The second metric was the bandwidth estimation counter, which just tracks the patterns of increasing, decreasing the sending rate, which is usually used to probe for more bandwidth by the algorithms. So now if we go back to our example, as cubic enters the congestion avoidance phase, it keeps increasing its sending rate. Consequently, aggressiveness increases. And when it reaches a certain threshold that we see here, BFair will reclassify this flow as a loss delay flow. Next, the same process continues. And eventually, cubic will start filling the queues again. And when it reaches another threshold, we can reclassify it again into the next group. So the loss-based group, where it actually should belong to. And it will remain here until its completion. Similarly, if you look at, for example, a BBR flow, at the beginning, it starts also as a short-lived flow until it reaches its BDP, when it's reclassified into, again, the delay-based group. So like cubic. And it remains here until, again, so the same way as cubic, aggressiveness keeps increasing, and it's reclassified into the delay-based group. Loss delay group. However, in contrast to cubic, we can see that BBR has this pattern of increasing, decreasing the sending rate that we can see here. And due to this, the bandwidth estimation counter will also increase. And when a different threshold is reached, this flow will be reclassified into the model-based group. So in this case, this threshold was set to 2, but we can see that BBR then is classified as model-based flow and remains here until the end. So I mentioned there are a few thresholds here that need to be set. So BFair, before being deployed, needs to be tuned. And this process somewhat is explained in the paper. However, so basically these parameters determine how fast a flow is being classified into a certain group, but also the accuracy. But for example, if you look at BBR here, we can see that if we set the threshold higher, we would still eventually detect it. However, it will take longer. This, of course, is a general idea, and way more details can be found in the paper itself. So now I'm going to go to the second BFair module. So that's the reallocation module. So the main purpose of this module, this module performed two important tasks. First, it stores the estimated group, and second, redistributes the queues between the group. So we will first start with the first task. So the decision to queue a packet into a certain queue so that this packet is processed with all the other flows that use similar metrics must be made in the ingress. So before the packet is even queued into the middle block. However, the decision to reclassify the flow can be made in the egress too. So after the queue stats are known, which we can see here. So if we can see a problem here. So because from the egress, we can no longer update the register that stores the group that must be allocated, in this case, in the egress. So before the queues, before the packet is unqueued. To solve this problem, we decided to recirculate all these packets back to the ingress. So all the packets that actually trigger a group update for a flow are recirculated back to the ingress, and the group is updated upon reception of these packets. Further, the second task of this module is executed, which is the reallocation algorithm. So the main purpose of this algorithm is to adapt to the current network state. So it favors groups with most flows by assigning more queues to them. Just in essence, it tries to make sure that each queue processes the same amount of flows. So this way we can use algorithms such as round robin. So I'm going to explain the reallocation procedure on a small example. More details can be found in the paper, but here I'm only going to go through a simple example with only two groups. So to reclassify a flow that belongs to a delay-based group, together with all the other delay-based flows, and all loss delay flows together with all the other loss delay flows, we need to calculate the parameter L1, so the border between these groups. So now, if you assume that at some point in time we receive an update packet that we see here, so this is a short-lived mice flow that was now reclassified into the delay-based group. So to estimate L1, we used a set of counters that we associated with each long-lived group. So counters C1, and every time these update packets are received, we either increase or decrease these parameters based on the new and the previous group. So in this case, because the new group is the delay-based group, we decrease the parameter C1, as this group basically gained a flow. The previous group was mice flow, so we don't have to do anything because it's a short-lived flow. And now if certain set of conditions is met, so basically if C1 is equal to 0, which means that all queues assigned to the delay-based group are utilized just right, while the queues assigned to the loss delay groups are underutilized. So FPQ here means flows per queue. So it's the average number of flows that are assigned to each queue. So basically C2 has C2 bigger than FPQ means that the loss delay groups has very few flows that are queued. And in this case, L1 will be increased, as we can see here. And this way, the delay-based group will gain a flow on the expenses of the loss delay group. Similarly, if another moment in time, another packet is received, we do the same process. So in this case, this is an actual delay-based flow that is being reclassified as a loss delay flow. We again try to determine the parameter L1. And so we perform the same operation as before. So we increase a set of counters. In this case, as a new group is loss delay, we decrease counter C2 while we increase C1. So basically, delay-based group gained a flow while delay-based group lost a flow while loss delay group gained a flow. And again, if a similar set of conditions are met, we will decrease L1. So at the expenses of the delay-based group, the loss delay group will gain a flow. Now, of course, this is a simplified version with only 2 groups, but can be extended to include more groups, so 4 in our case. But of course, some special cases need to be taken into account, which some details can be found in the paper. And of course, there are special cases. So for example, if FPQ changes, we need to update all the counters. And so more details can be found in the paper. However, the outcome is important. So the outcome of the reallocation algorithm is that all the queues are assigned to a specific group, as we can see, and that all packets that are actually queued belong to the flows using the same congestion control algorithm. And finally, we have the last BFair module, which is the apply action module. So the main purpose of this module is to enforce fairness among flows that are processed within the same queue. So we decided to do this by applying custom actions based on the group. So there are 2 important reasons to apply actions to flows. First, even flows that use same congestion control algorithms can have low fairness if RTTs are different. And second, even flows that belong to the same group don't actually have perfect fairness, as we saw in some of these pictures at the beginning. And we decided to also use different actions, so to target each group specific. So we apply actions based on the group. So in this way, we are also able to target different metrics. So for example, for delay-based algorithms, we actually try to target delay. And for example, for some algorithms that don't even react to loss, we also target, there are also algorithms that don't target they don't react to loss at all. And for these, we also have different actions. So here we see the 3 actions. So delay, packet, drop packet, and adjust the receiver window. More details can be found in the paper, but due to time constraints, I will not go into all these details here. So finally, I want to go to some of the main results we had. So we did evaluation using Mininet and using a barefoot switch. So hardware setup with a few servers that were connected to the one barefoot switch. Additional details also on tuning can be found in the paper, but I'm only going to go through some of the interesting results concerning fairness. So we compared our solution, so BFair, to a solution that uses no mechanism to enforce fairness, no AQM, and a solution that queues packets into queues based on the hash of the flow identifier, so different queues. And furthermore, we tested 2 versions of BFair. So first one was idle BFair that combined the first 2 modules, so the reallocation and fingerprinting, and normal BFair with all the 3 modules, also including apply actions module. So we can see here that in all the analyzed scenarios, BFair was able to outperform the other solutions, especially when we compare BFair to a solution that distributes flows based on the flow identifier. We can see that the interfairness of flows, so their good interfairness properties, can be used to their advantage, and that the fairness is usually higher. In addition, if we compare BFair and idle BFair, we can see that when the number of flows was very small, the 3rd module was not needed because, of course, the number of flows processed inside a queue was really small. So there was no actual competition. Finally, we also tested the RTT fairness, and we can see that BFair can improve the fairness here and also outperforms the comparison baselines. However, the performance does decrease with when the difference in RTTs increases, which we see on the left side of this figure, right side of the figure. So finally, to conclude, in this paper, we developed BFair, which is a BFair solution that tries to determine the group of the algorithm directly in the data plane. And our results show that distributing flows based on their congestion control group can significantly improve fairness in the network resource utilization, so that flows will share resources more fairly. Thank you.
Okay, great, thanks. We have time for a few quick questions. Any questions for Belma? Yes, KK.
So I was wondering if there is any action you might consider if you had flows that were responsive to a explicit notification from the network.
Yeah, so I did not test it, but that can easily be added. So I think that would be even a better option if then hosts support it, to use it for example, even loss-based algorithms.
Because BBR has evolved to support that explicit notification?
That's true. So it can. So basically the action, it's totally modular. So different actions can, of course, be used for different algorithms. So I think through BBR, there was a new version that actually now does react to other stuff, so which is nice. So then actually these actions can be used. I agree.
Thank you.
Okay, any other questions? We have time perhaps for one other quick question.
So this fairness index that you have is relatively coarse. And if you actually look at the dynamics, you end up seeing that a measure of 0.9 something can actually result in behavior that is quite unfair on a transient basis. Have you looked at how your flows behave with respect to time?
so I did, when we did the results, we did export all these statistics. So indeed, this is the average fairness index. So there are some dynamics there. And so I did look into it, but there was space constraint to actually include this into the paper. But yeah, of course, the fairness index can vary actually a lot. So especially in the beginning. So basically there was also parts where flows are not in their correct group. So then it can also go down at that point. So of course it varies in time.
Thanks.
Okay, thank you. I see that some people are having some issues with seeing the screen. If you go to the chat, you will see that Xing Wang has posted a link for Zoom. You might want to try it with Zoom, and just feel free to speak up if you're using Zoom and you still have some issues with seeing the screen.
Okay.
Okay. Well, Belma, I think there's no other questions, so maybe it's a good time to move to the second paper, which is Oktopus. So Khaled Diab will be presenting the paper. He has received his PhD from Simon Fraser University in 2019, where he's currently working as a research associate. His research interests are in the intersection of systems and networking with the goal of making the networks and applications more efficient. Examples of his recent research include multicast protocols, service chaining, cloud gaming, video streaming, and content distribution networks. Khaled, if you could share your screen.
Yeah, I cannot share my screen because Belma is still sharing hers.
Belma, I think you will need to stop sharing your screen.
Now you can share your screen.
Okay, thank you. Hello? Okay. Hello?
Yes, we can hear you, and we can also see your screen.
Okay, perfect. Should I start now?
Yes, let's begin.
Okay. Hello, thank you, Soudeh, for the introduction. My name is Khaled, and in this video, I will talk about Oktopus, which is a new algorithm to address the service chaining problem for multicast traffic. Today's internet applications allow anyone to produce content anytime at high rates. Examples of these applications include Twitch and Facebook, where they actually enable millions to stream their live videos or sessions to millions of concurrent users over the internet. Interestingly, these applications naturally exhibit one-to-many communication pattern from a single source to multiple destinations or receivers. So network operators can use multicast to efficiently support these applications and reduce the network load on their networks. In addition, network operators also aim at maximizing the total number of admitted sessions so that they can achieve their business goals and more profit. Meanwhile, network operators deploy middle boxes to their networks to perform several network functions like firewalls, intrusion detection systems, and so on. And to reduce the cost of purchasing and managing these middle boxes, operators often virtualize and run these network functions on general purpose servers. And then they deploy these servers, including the virtual network functions, at different ISP locations to support their customers. In our work, we refer to these virtual network functions as services. For many multicast applications like video streaming or maybe gaming applications, traffic of a session may need to pass through a set of order services before reaching its destinations. As a result, network operators need to calculate different paths compared to ones, for example, like shortest path flows or paths. so that they can actually support and provide the required services per multicast sessions. For example, if we consider a session from source A to the green receivers on the right, and this session requires the three services, a firewall, an intrusion detection system, and a video encoder, assuming maybe this is like a live video session, then the network operator could calculate such a path to support these services before reaching the applications. For example, the black and blue and green ones, so it will support all the services till it reaches the nodes F and G. And then for the other receivers, it will calculate these paths to support I, J, and K receivers. A very important observation is that packets of the same session may traverse the same node or link multiple times before reaching the destinations. So this actually results in more complex structures compared to the regular multicast trees that we are familiar with. And we refer to these new structures or the complex structures as multicast distribution graphs, which are basically the graphs that its paths provide and support the services required by the session. So the problem that we consider in our paper is that given a set of multicast sessions and their bandwidth and service requirements, our goal is to calculate the multicast distribution graph such that we minimize the total routing cost on the network. Such that the link processing and forwarding table capacities are not exceeded. The main challenge in our problem is the large search space in this problem, because we don't impose any assumption on the network size or shape, the traffic pattern, or the service chaining requirements. So basically the search space basically explodes. We studied the hardness of this problem in the paper, and we showed that even a special instance of this problem is NP hard. Maybe another aspect is that prior work showed that this problem cannot be approximated within any ratio, even if service chaining is not required at all. And even for unicast, even if we have the infinite processing capacities, this problem is computationally intractable. So we have a practical and important problem, but at the same time, it is very hard to solve practically. Or in a reasonable time. So our approach is we develop and design a principled heuristic to calculate the multicast distribution graphs efficiently. So we propose a new algorithm called Oktopus. It is a new path-based approach to solve the multicast service chaining problems. Oktopus is built on three design principles. So the first one is reducing the search space, and this is to make the solution practical and run in reasonable time. And this is done by dividing the computations of the algorithm into offline and online phases. And then the second principle is the recursive composition of services. And this is basically to efficiently support long service chains, which can occur or happen in network operators or in some sessions. And this is done basically by piecing together smaller paths to calculate the final path that support all of the services. And the last principle is the fine-grained control over chosen links. And this is done to find efficient solutions that achieve some objectives like load balancing. And this is done by carefully weighting the links before we actually choose them or while we are doing the search. So now I will give an overview of Oktopus. So as I have just mentioned, Oktopus consists of two steps or two phases. The first phase is the offline phase, which generates the segments. And the second phase is the online one, which calculates the actual multicast distribution graphs. So in the first phase, we we are given the actual network ISP topology or network topology, and for each node pair, let's say A and C, we calculate a set of loop-free sequence of nodes from the node pair, let's say from A to C. And once we find all of the segments across all the node pairs, we maintain them in a structure that we refer to as the segment store. And then in the online phase, given the sessions themselves and their requirements and the segment store, we calculate the graphs by searching in the segment store itself. And this is done by calculating or carefully calculating weights on every link in our segment store, and also applying the recursive composition if we cannot find such a path in our segment store. And the recursive composition allows us to find paths that are not there in the segment store. So now I will sorry, and then after we calculate the graphs, and sometimes we can update the segment store so that we can accommodate or account for the dynamic nature of the network in terms of bandwidth changes. Now I'll briefly talk about the two phases of Oktopus, and the paper includes more technical details. So in the first phase, which is done offline, the goal is to pre-compute the segments to be used in the next phase. And the main challenge here is the number of segments grows exponentially with the network size. So we cannot just enumerate and maintain all of these segments. So our approach to address this challenge is that we employ traffic engineering observation from traffic engineering literature, and we progressively add new segments if and when needed. And so the high-level overview of the generating segments algorithm works as follows. For every node pair in the network N and M, we traverse the network using breadth-first search, and then we compute the first k loop-free segments, and this should not exceed the given path length. And this is very important so that our multicast distribution graphs do not actually result in a lot of packet delays in the network. And then the second step, the third step, we compute a set of edge disjoint passes from N to M as well, after we calculate the segments coming from the breadth first search. And we do this by running an existing or any of the existing maximum flow algorithms. And after all of the segments are generated and calculated, we maintain and store them in our segment store, which again can be progressively updated and modified during the online phase. During the online phase, which calculates the distribution graphs, for every session and for every destination, Octopus calculate a path from an existing path to that destination. So Octopus maintains a set of paths for each multicast session that it actually calculated. And for any new destination, it tries to connect that destination to these existing paths. So I will run a simple example to show the high level idea of the online phase. So let's assume we have a session with the source S and two destinations that requires two services. And then a set of calculated paths is still empty since we still didn't find any path. Our first step is to search for a path from the source to destination A. And then we weight these links and we pick the minimum cost path that provides the services 1 to 2. And once we find this path, we add it to the set of found or calculated path by Octopus. And then in the next step, when we search for the destination B, we use all the nodes in the set of calculated paths to try to find the node that will connect the destination B to. So for example, we have some paths that we can look at from node A to node B and so on till we reach from node S to node B. And then similarly, we pick the minimum cost path as well. and once we find it, we add it to our set of calculated path, and then we merge these two paths together. The most important thing to notice or to observe is that Oktopus here ensures that there is no forwarding ambiguity will happen, and this is done by tracking the packet types at every router, at every interface at every router. So in cases where we cannot find, or the algorithm cannot find the segment directly that provide the services without exceeding the resources, we apply the recursive composition mechanism or technique. And the main goal here is to extend the search space beyond the segment store. Let's assume we want to look up for 3 services from 1 to 3, and we have the source S to destination D. But unfortunately, we couldn't find such a path that support the 3 services in our segment store. So we pick the path with the maximum number of services, assuming that this is S, I, and D. And then we connect that path to a node that's supporting the next service, which is 2. And notice that the links or these dashed links do not actually exist in the segment store. But this is how we extend our search space beyond the segment store. And then given these 3 nodes, we pick the one that results in the minimum cost. And then we recursively search from the chosen node, let's say it is K, from the destination D. And we recursively apply the same algorithm till we find the actual path or the final path that supports all of these services, 1, 2, and 3. To evaluate our Octopus, we implemented Octopus in 2 main components: an optimization engine which runs the actual algorithm. The optimization engine receives the network data from control plane frameworks, and then we write an API or enable network developers or operators to write network applications using our APIs to represent their requirements. And then these requirements are communicated to our optimization engine. And once we receive these requirements, we calculate the paths, the distribution graphs. We send them back to the control plane framework, which distribute the states or the state entries to the network switches. Our implementation and data sets are open source, and we also provide environments or reproducible environments so that the community can rerun and experiment with our Octopus. To evaluate our algorithm, we compare it against the optimal algorithm implemented in CPLEX and the closest algorithm in the literature, using 5 ISP topologies with different sizes. And we are interested in 5 performance metrics: the percentage of allocated sessions, the routing cost, since it will show the network load, and the graph size, which represent the packet latency in general, and then the running time, which will represent the practicality of these algorithms. So first, we show that the optimal algorithm is not practical for realistic scenarios. For example, optimal fails to produce any graph for 50 concurrent sessions, while Octopus calculates valid graphs in only 1.2 minutes. Also, we show that Octopus is close to the optimal algorithm when the optimal could produce some solution or produce a solution, So for example, for 10 concurrent sessions, the routing cost optimality gap is only 5% on average. And more importantly, the running time of Octopus is only 6 seconds per session, while it is 1.4 hours per session for the optimal. So optimal cannot be run in reasonable time. We also compare Octopus versus the closest algorithm called MSA. And in the paper, we show many scenarios to showing that Octopus outperforms that algorithm across all the considered scenarios. For example, here we change the percentage of receivers from 10% to 40%, and we observe that Octopus outperforms the MSA by up to 37%. And similarly, when we change the service chain length or increase the length from 2 to 6, Oktopus can or outperforms MSA by up to 30%. And this is basically because we weight the links carefully because since we have fine-grained control over the chosen links, and because we implementing and designing the recursive composition approach, which allows us to reach more services than the other algorithm can reach. So in terms of the running time, both algorithms are very close to each other. So basically, Oktopus is practical in most realistic scenarios. In terms of the routing cost, Oktopus and MSA are similar. So Oktopus does not overload the network compared to the closed system in the literature. And Oktopus graphs are larger by 2 links on average. This is because actually Oktopus could reach or allocate more sessions. So it needs on average more 2 links to reach all of these destinations and allocate these more sessions, which means that Oktopus does not or impose negligible packet delays on the sessions. To conclude, Oktopus is an algorithm to solve the multicast service chaining problem. It is a path-based approach that systematically reduces the search space. Compared to the optimal, it is very close to it in terms of the performance, and it is fast and practical. Compared to the closest algorithm, Oktopus can allocate more sessions by up to 37%, while it does not overload the network and impose negligible packet delays on the sessions. Thank you.
Great, thank you. We have time for some questions.
Hi, can I ask?
Sure, go ahead, Bing.
Yes, for the first part, trying to find the segments, right? You said trying to find the multiple edge disjoint paths between N and M, and
Yes.
you use the maximum flow algorithm. So I can imagine the reason you use that is because probably, yeah, of course, it's an efficient optimal algorithm. And of course, then you are not trying to find the optimal algorithm, right? So here, so my question is, what is your rationale using the maximum flow? Because the maximum flow only here, probably you're assuming each the bandwidth of each edge is they're all the same, right? So
yes,
yeah. So can you
yes.
give me?
No, it's here. It's not about the bandwidth. This is done offline before even we have any thing related to the network in terms of the sessions or the bandwidth. So this is just look at the structure. So the main idea here is that actually, excuse me?
Oh, no, it's okay. Continue.
Yeah. So we actually have 2 phases here. So it's step 1 and 2 in one phase, and step 3 is in another phase. So in the first phase, we traverse the network using breadth first search. So we actually calculate some segments here, right? But the breadth first search actually, it's good in terms of reachability, but it does not add a lot of diversity to our segment store. So we applied or we want to find some edge disjoint passes in the network itself. So disjoint in terms of the segments that we already found in step number 1 and 2. So once we
so my question is that if you use the maximum flow to find the edge disjoint path, there must be some strong assumption of the.
No, it's just we are looking at the structure. Like for example, we assign each link weight 1, right? So
Yes.
and right. So we
yes,
here
yes.
we just look at the structure, not looking at the bandwidth itself. So looking at the bandwidth or checking the bandwidth will be done on the online phase. And if we sense that we need more segments, we'll try to generate more segments, or we will use the recursive composition.
Got you. Okay, thank you very much. Very nice. Thank you.
Okay, great. Other questions? Okay, well, in that case, let me ask one question. Does Octopus support this updating these distributed graphs, right? Like, for example, migrating some of the paths because some of the nodes migrate or the load changes? And specifically, I'm wondering about the ordering of packets, right? Because some of these network functions like firewalls or intrusion detection systems, they are sensitive to the correct ordering of packets. So if you move some of these paths, how do you deal with enforcing the correct ordering? Do you need to synchronize?
So what do you mean by moving or migrating the path?
So you're computing some of these paths between different nodes, right?
Right.
Now, suppose that, for example, the load on the network changes or some of the nodes move and migrate, and you will need to update these paths.
Yes.
So that is what I mean by migrating the path, moving it from one path to the other, moving the traffic from one path to
Moving the traffic, okay. So I cannot see why there could be a problem here, because here in this step, we make sure that the packet ordering, I don't know, do you mean like the ordering, for example, I wanted service 1 and 2, but we result in service 2 and service 1, for example?
No, not for the ordering of NFs, for the ordering of packets inside one flow.
Oh, I see. No, we don't have guarantee on this, unfortunately.
Okay, I see. Thanks.
Yeah, so any specific reason? I understand that it is important, obviously, but
yes, for some type of network functions, it is important, right?
Sure, yeah, it is. But for example, I would assume that this multicast will use UDP. So, I mean, packet ordering, I mean, we're not touching anything related.
Support UDP.
Excuse me?
It depends on you using UDP only. You can support TCP.
No, in multicast, we cannot use TCP. TCP is connection oriented.
Right.
So in multicast, we only run UDP, or at least let's say vanilla TCP cannot support multicast.
Okay, I see. In that case, it seems like that you will have also some assumptions for the network functions, right?
Exactly, yes.
Okay, cool, thanks. Any other questions?
Just one last question. Normally NFV deployments are used in scalable scenarios. So what if you have a heavily volatile NFV scenario, like NFVs are coming and going? So how does that change the load on your computation? Because depending on the demand on the network, the NFVs are going to either scale up or down. And
yes.
If they scale up, you have different nodes. If they scale down, again, they don't exist anymore. So what happens with the load on your computational load at that point?
Yeah, thank you for the question. That's an interesting one. So basically, since we keep track, like if you can see my slides here, so we keep track of every path from each source to each destination, and the connection between these paths. So if we find, for example, that the service number 2 on node K does not exist anymore, we'll try to find another path from, let's say, from one of these existing nodes to the destination B. So it's as if we will repeat some parts in the algorithm, but after updating the available resources.
Okay, so you're not doing the entire computation again, but you're doing partial computation based, like partial path computations. And
yes, exactly. Yes, and this is embedded in the algorithm itself. I mean, we don't need to change the algorithm because this is how the algorithm works.
Okay, cool. Thank you.
You're welcome.
Okay, great, thanks. We have time for one more question. Okay, it seems like that there's no more question. Well, in that case, I can ask the final question too. So you are focused on ISPs, right?
Yes.
I was wondering if there are any reasons, any parts of your design that is optimized for this context. Like, for example, I can imagine that this can be useful in other settings like data center networking, for example, as well, right? Of course, you can mention that it is mostly TCP, but there might be ways for running TCP over UDP as well in data center networking and cloud computing.
Right. So it could be, but here, like we assumed like generic graph. So for example, I don't know, like if in data center networks, we usually have the leaves, have the servers, like because it's tree based. So probably it will end up with, or at least our algorithm will probably produce a solution, right? But I don't know about the performance of, or like the performance of that solution. There is no specific assumption or reason why we chose ISPs, but because usually like in most, like for example, we assume that like the network operators need to apply some external services or some services on the packets coming from the outside. But in data centers, I think most of the packets are like kind of running inside the data center itself. It seems to be like internal to the data center. So I mean, the operator or data center operator, I mean, owns the thing. So he or she or the developer can write their own services before, like at the VM itself, at the source. And once this is applied, we can run the packet or forward the packet to the destinations.
Okay, thank you.
I don't know if this could be the model, but unless you have something else in mind that these services can be run actually in data centers.
All right, great, thanks.
Okay.
Any other questions? Okay, in that case, let's move to the final paper of this session, CoNICE. Mohamed Jahanian will present this paper. Mohamed is a PhD candidate at the University of California, Riverside. He is in his final year of PhD and will be in the job market soon. His research focuses on information-centric networks, formal methods, and distributed systems.
Can you see my slides?
Yes.
Thank you, Soudeh, for the introduction. Hello, everyone. My name is Mohamed Jahanian, and I'm going to talk about our work called CoNICE on consensus in intermittently connected environments by exploiting naming, with a focus on application to emergency response. This work has been done in collaboration with Ramakrishnan at UC Riverside. So in many scenarios, such as during disasters, we may need to disseminate information in an intermittently connected environments where the infrastructure and the traditional means of communication and networking is damaged. One application is when we have many users, such as first responders during disasters, that create updates to a shared data set, such as data on a map. In this situation, consistency and the order of applying those updates is important and yet challenging and complex. So we present CoNICE, a framework to ensure consistent dissemination of updates among users in such environment. We support multiple levels of consistency, including both causal ordering and consensus. A novelty of our work is the integration of consistent dissemination with naming of information for two purposes. One is to enhance the relevancy of such dissemination, which is the typical benefit of using naming in information-centric networking paradigms. And secondly, we also use it to enhance the degree of information consistency among these relevant recipient users. We focus on an example application, which is map geotagging in emergency response. We divide our map into regions, each region having its own tasks during emergency response. This is a common approach in terms of regioning in online gaming and AR, which we use here for emergency response. The regioning can have a hierarchical structure. This gives us a multiple levels of the geographical view, which different users can view at certain levels by zooming in and out. We capture this hierarchical structure in a graph-based namespace. First responders indicate their interest at their desired granularity by subscribing to subsets of this namespace. The subscription has a hierarchical form. So for example, subscribing to R11 means an implicit subscription to all of the descendants of that node, including R111, etc. Users create region-bound updates in the map geotagging application. The updates can pertain to pins and shapes with information associated with them. A pin can be about, for example, marking a building or house as search and rescue completed, or evacuation on a certain point on the map. Or it can be a shape of any size, for example, to note that this area needs a firefighting team. We assume that every first responder is bootstrapped to have the map background or base layer offline, and also the namespace. Our goal is to have updates, which is the data layer, created and disseminated dynamically to the relevant recipients according to their namespace subscription in an online manner. This can be an easy task in normal situations with the network infrastructure, but it can be challenging in disaster situations, where we assume that we have no central coordination, no network infrastructure, and no time synchronization between users. We assume that the network is fragmented, which is there may not be a path between two nodes at certain times. So nodes and users rely on device-to-device communication and opportunistic exchange of messages. For example, here users A and B are in one fragment, while C and D are in another. Assuming user A creates an update about R111, how can it reach C and D? So if user B moves towards the other fragment using opportunistic or delay-tolerant networking propagation, the other fragment users can receive the relevant information, in this case, users C and D. The use of namespace makes sure that relevant subscribed users are notified and can participate in the dissemination. We can have many users that create many updates without having a centralized coordination. These updates are on a single shared data set, which is the map data layer. Each update can be about adding, removing, or modifying pins or shapes. The order of applying these updates at recipients matters in the result, which is the final map view on individual first responder devices, because we can have multiple users creating updates concurrently. And consistency of updates is important and challenging. So our goal is to have eventually all users, relevant users, have the same view of the map. The strong consistency can be achieved through consensus or agreement on the order of updates in each region. This consistency requires complex and time-consuming procedures. So CoNICE provides a flexibility of multiple consistency levels bound to named regions. So we propose 3 levels of consistency. The first one, or level 0, is replication, which is to make sure that users receive all updates. The gossiping module and protocol takes care of this level. Then we have consistency level 1, or causality, to make sure users get causally ordered view of updates, which we call moderate view, taken care of by causal ordering protocol. The level 2, or agreement, makes sure users get an agreed upon view of the updates in a strong view used by consensus. To achieve selectiveness, we add name-based interest profiles, or NBIPs, for each consistency level, meaning we have NBIP 0, 1, and 2. Each NBIP is basically a named subscription, and a subscription to a subset of the namespace to limit a user's participation according to the relevancy of tasks for that individual user. So we have 3 levels. Each has a sequence in terms of in form of a queue and slots of it to fill. And each queue is bound to regions, and they are filled incrementally. Here we have 3 users, U1, U2, and U3, and they receive updates, A, B, etc. And the dependency of the updates is indicated as, for example, B over A means B depends on A. This is to note the causal relationship between updates. The level 0 replication is what the gossiping protocol takes care of by propagating updates. Gossiping in a DTN environment is probabilistic, meaning there's no guaranteed delivery, and also it can be out of order. So users fill this levels queue in the order of receipt of the updates. So to capture causal ordering, we add level 1, which uses the output of level 0 to form the input for the level 1 queue, to form the moderate view. This level takes care of ordering the orderable updates in a deterministic way. For example, A and B, in which B deterministically is dependent on A. So this is a good starting point for useful view in practice, as we have causal orders in the view that users have. But the challenge is that this doesn't order unorderable updates. For example, C and D, which have no causal relation. And this can happen when even we have two potentially related updates, but because different users create and receive these updates concurrently and without coordination, some users may not see all the already created updates that are potential dependencies. So because of that, we add level 2 agreement on top of it, which is the consensus module, and applies the Q1 elements in an agreed order to form the strong view. Here we see that all users eventually form the same sequence, and they order even the unorderable updates. Even C and D here, we see that it's exactly the same across all the different users. So we design protocols and ways to identify information in messages for each level of consistency. We define each update as to belongs to exactly one region, which is the smallest region large enough to contain that update on the map. For example, here, update A belongs to R111, while B belongs to R12. So we identify an update as a tuple, including information about the user ID of the creator of that update, the region the update belongs to, and a sequence number. We can have additional fields such as regions covered to include R122 and R123 for B as well. So at level 0, we use a DTN-based epidemic routing protocol for gossiping, where users exchange states from their buffers, the messages that they have buffered, and the actual messages whenever they come into contact. We enhance it with name-based relevance. So users only exchange messages of interest using their level 0 name-based interest profile, or NBIP 0. This way we can achieve mutual replication of relevant updates between two users that come into contact. The update is collected by the subscribers of its region set and above that. For example, subscribers of R12 and R1 are interested in update B and will receive it. In level 1, or causality, we use causal ordering. The goal is to capture the causal relations of updates to form the moderate consistency and view. The causality has been proposed by the happened before relation, where, for example, one user sends M1 and then sends M2, which is the FIFO order, or user receives M1 and then sends M2, which is the local order, or a transitivity rule. This defines a logical way of defining a causal relationship. Logical clock and its extension vector clock is a popular and established method as a mechanism to ensure causal ordering. Vector clock carries a causal history of a message inside that message for this ordering. For example, here we can have different nodes or processes P1, 2, and 3, each with initially all 0 vectors. Each vector element pertains to one user, and how many messages that user has created. If P1 creates message M1, it increments its vector once, and P2 compares the received vector, it's one step ahead and accepts it. If a new message M2 is created and sent to P3, P3 before receiving M1 does not accept M2 and puts it on hold because the vector is 2 steps ahead. When M1 is received, then P3 accepts M1 and M2 in that order. This is how vector clock blocks messages for which the dependency is not yet satisfied. So we use a similar method, and we optimize the causality relation definition by saying that messages are causally related if one is happened before in the same region. And for that, we use the namespace. And also the amount of causal history that is being carried in each message only is bound to that particular region. And for this purpose, users include the dependencies of the same region up to the point that they have seen in the header of the message that they sent out. So the format is shown here, and we support 2 types of dependency, implicit and explicit. For implicit dependency, we use sequence numbers for each user and region pair for the same user and same region tuple. For example, U1, R1, and 3 precedes U1, R1, and 4 to support FIFO ordering. Explicit dependency uses an explicit set of references. These are the updates that identify other users' updates on the same region to ensure local ordering. We also add a reactive mode at the recipients where instead of waiting for dependencies to be received, reactively users send a request if they detect causal gaps. For example, if a user receives U1, R1, 4 but doesn't have U1, R1, 3, it requests for U1, R1, 3. Any user with the information cached and buffer can respond. It doesn't have to be necessarily the creator of that update. Only users that have relevancy in their level 1 name-based interest profile or NBIP1 will participate for this procedure of reactive requesting and responding. In level 2, for agreement, we use consensus. And the consensus protocol is used in a total ordering mechanism for strong consistency. The goal of consensus is to achieve agreement between a group of nodes on a value. The value here in question is the next update to apply for each region slot pair, which orders even the unorderable updates in terms of their causality. So there are classic consensus algorithms such as Paxos and its implementation Raft. Paxos uses multiple rounds of leader election, voting, deciding, and disseminating decision. In Paxos, we have one leader which has to be elected, and other nodes are followers and observers. The common case in Paxos is to assume that we have a connected network with reliable links and synchronous or eventually synchronous environment. This has been argued to be not very suitable for highly transient networks, where we have assumptions that are different, where we have not, we don't have reliable links necessarily. So simply using Paxos in intermittently connected networks may result in many frequent reattempts of sessions, which can cause a lot of overhead. So there have been consensus algorithms that tolerate loss and unreliable links for this kind of environment that we are considering. They assume a synchronous environment, although with good periods, where a message is eventually reachable to any node except for permanently crashed nodes. A notable example of these algorithms is the 1/3 rule, or OTR algorithm. OTR is coordinator-less, so we don't need to elect a leader. Every node can contribute or vote and decide. The decision can be reached on a 2/3 majority rule, So every node participating has to know the population count to calculate this majority. It allows 1/3 of nodes to fail in one round and still be able to reach a decision. The decision is same across all users, which is the agreement property. It can go through multiple rounds, but has the potential to finish in a single round. Also, it has been shown that consensus in an intermittently connected environment can take a long time because of a lot of frequent disconnections, and we may need to wait a long time for a path to reappear. So we use OTR and enhance it in a number of ways, some of which I will mention. One is the use of name-based selective consensus participation. So rather than having all users in the network participate in consensus, we use level 2 name-based interest profile, or NBIP2, at every user to determine the participation. So we may have name-based groups within the whole population to participate. For example, for slots of R11, only the subscribers of R1 and R11 participate. Other users can still help with relaying and propagating the contribution and decision messages if it is allowed by their NBIP0. So this flexibility of having multiple NBIP levels can help with having this granularity. We also had periodic reachability beaconing for population count estimation. So as I mentioned, we need to know, each user has to know the number of participants. So rather than a known fixed count for all users to count a majority, we periodically announce each user's ID and its NBIP2 subscription. So each user estimates the number of subscribers for each name-based group. We also add support for decision invalidation when we have long-term fragmentation. So we may have very isolated network fragments, such as when we have 2 shelters during disasters that get connected after a very long time where a path appears. So this may cause different decisions from the 2 fragments for the same region slot pair. This will violate the agreement property. So rather than assuming good period in the whole network, we support good period within fragments, and then allow for invalidating of already decisions made when when members of the 2 fragments start interacting. When there is a tie and a contention, the decision from the higher populated fragment wins, and the other should be updated and will follow. So here, this is the format of a contribution message for user X for region R11 and the first slot of it, and assuming that it proposes the value A being an update to fill that in the first round, when assuming that it has seen N participants for this name-based group. This contribution is disseminated to subscribers of R11 and above it, including R1 as well. Users create contribution either via initiation or triggered when receiving contribution from other users. Also, when a user enters a new round of consensus, it deletes the contributions of previous rounds for better management of storage and using less buffer. A decision message also includes this information and the decided value. It is disseminated to subscribers of R11, as for the example here and above it. Users decide and create decision message by either reaching the 2/3 majority rule locally or receiving decision messages from others who have reached the decision. So one by one, as users get notified of decisions, they build up their snapshots, which is their strong view based on region slot decisions. And there are more details and corner cases of this protocol and proofs, which are included in our paper. So to experiment, we did a simulation on a city scale, subset of a city of Helsinki. And we divided into hierarchical regions captured in namespace with a city, major district, district, and neighborhood hierarchical format. The subset that we focused on is the southern major district that has 3 districts, and the size is 4,500 in 3,400 meters. We put 30 mobile first responders, 10 for each district. We added additional benevolent mules, 500 civilians and 50 vehicles to help with the delivery of messages. These mules do not participate in consensus. They only help with propagating information. Each first responder creates 3 updates. So in total, we have 90 updates. We implemented our protocol and performed our experiments in the one simulator. So first, we focus on levels 0 and 1, gossiping and causal ordering. As we can see here, with the use of naming, which is both named regioning to include the region ID in update headers, and also name-based interest profiling at recipients and subscribers, and also the use of reactive causal ordering, we see higher replication completeness of relevant information or deliveries, and also causal completeness, which is how many causally ordered messages are delivered at first responders. This is a small enhancement, but still we see that we achieve better average latency in both cases as well, with similar number of total relays indicating the total network traffic. So CoNICE's naming leads to more efficient gossiping and causal ordering. But the real benefit to a much larger degree is shown when we talk about consensus and the level 2. Comparing the use of name-based interest profiling versus not using it, we see here that in this 12-hour simulation scenario, our method reaches much higher completeness of agreement in terms of relevant messages that are received. Also, we see that our method uses much less buffer to achieve this much completeness. So as shown here in the diagram, with the use of naming, we achieve higher agreement completeness of relevant information by up to 100 times, which is due to the fact that using NBIP2, we can identify groups and selectively limit the participation of consensus sessions. We also have more relevant decision deliveries and better latency at the first responders, up to 2 times. Also, we can note that the high absolute values of decision times justifies having a moderate view in the meantime for causal ordering. Also, our method uses less buffer at first responders, up to 5 times because of naming, and similar number of total relays in the network. This shows that CoNICE's name-based grouping achieves agreement in a more efficient and effective manner. So to sum up, we presented CoNICE, a framework to ensure consistent dissemination of updates among users in intermittently connected environments, focusing on the application of emergency response. CoNICE provides multiple levels of consistency, supporting causal ordering and consensus, which is a flexible trade-off between completion time and degree of consistency in situations such as disasters. We also have multiple level naming schemas for fine-grained subscription, which reduces the user storage in D2D buffering, and also achieves higher completeness of strong consistency and faster consensus convergence across the relevant users. Thank you very much, and I'd be happy to take your questions.
Great, thank you. We have a few minutes for a couple of quick questions.
Hello?
Okay, I can't see any raised hand in Zoom and also no questions on Hova.
There's one question, Soudeh. It's
Where?
from Khaled.
All right, Khaled, please go ahead.
Yeah, sorry. I just have one question. So what about the power consumption of your new algorithms when it
Right.
because they use like mobile phones or cell phones, right, to do some transmission and maybe some processing as well.
Mhm. So we didn't directly investigate that, but I think so. With the use of selective processing, with the use of naming, users will, at least are expected to consume less power. For example, when we use the name-based interest profiling, instead of processing messages for every consensus session in the whole network, if you only process those messages that are relevant to you, this will greatly reduce the amount of power on devices that you will have. But we didn't directly investigate that aspect,
Yes,
but it is expected to have benefit.
So may I have a follow-up question maybe?
Sure, go ahead. I don't think.
Yeah, but so would that affect this selective processing? Would that affect the final or the strongest view of the consensus or no?
So
Or no?
the strong view is only at particular regions. So only if you are a user interested in a certain subset, you only care about the consensus in that or the strong view in that region. So with the use of our name-based interest profile, you can only limit your view to that particular region that you're interested in.
I see.
So
Thank
with
you.
that naming, you only, focus on, yes, thank you.
So Mohamed, maybe I can follow up with the issue about power, that given that you have so much less buffering that you have to deal with in comparison to the other approaches, you will in fact, as you said, you are forwarding less, you're also buffering a lot fewer packets. So naturally your power consumption should go down, right?
Exactly. And also you're processing less messages overall, yes.
Okay. Thank you.
Okay, great, thanks. Any other questions? Well, just one quick question. So you're listing 3 of the consistency levels that you focused on. I was wondering if you can briefly elaborate on this. Why did you select these particular levels?
Right. So these are so the different levels are picked based on the amount of completeness that they provide with the users and the complexity of each of them. So for example, we added level 1 as well as level 2 because level 2 gives the strongest view, but it takes a longer time because consensus is a much more complex procedure than causal ordering. However, in the meantime, while the consensus is being completed, having a causal view, a causally ordered view that is not that is not a strong consistency, but it is a midway moderate level of consistency, can still be helpful with the first responders who have real-time tasks to take care of. So each of these levels can have practical purposes, and it provides a flexible level of trade-off between complexity and completeness.
And also there is a natural building up of capability from one level to the other, right?
Right, yeah. Yes, we feed the output of each level to the input of the next level.
I see, okay. Thank you. So any other questions? we are almost out of time, so I think we will conclude this session here. Thanks to the speakers and those of you who joined.
Yeah, thank you everyone for